Good afternoon, class. Before we get to the lecture notes, I printed out a few slides from class that show the relationship between Q, K, and free energy. So here we have a diagram that shows the energy, which is this big curve here of our system. And this is the extent of the reaction. So pure A would be all reactants, pure B would be all products. This is the free energy of our system. And when we're at the bottom here, this is the situation where we have our system is equal to our equilibrium constant K. So what does this mean? Let's take a look at an example. This curve would be a situation where our equilibrium at the bottom of our energy well is closer to the reactant side of the diagram. And being at the bottom of this energy well shows that this is the lowest energy of the system. This is when the system is its most stable, and that is where equilibrium lies. For this situation, where it's kind of sloped over to the left, this is where KEQ is less than 1, which means we have small products at equilibrium, and our equilibrium lies towards the reactants. So if our product concentration is small and our reactant concentration is large, we have a small number divided by a large number, so we have a small equilibrium that's less than 1, and it's over here. We can now introduce the idea of Q and relate it to K. So using the same plot, here's the situation where our system, shown in this vertical black line, is further to the right and higher in energy. So this is a situation that is pre-equilibrium, where we have too much product. In that situation, Q is larger than K, as we saw in the notes previously. This will shift towards reactant A to become lower in energy. So if we have a situation where Q is larger than K and we have more products than we're supposed to, we can see that it's up and it's actually higher in energy. In order to shift to reach equilibrium, the system, this vertical line, has to shift towards the products going left. And when it does, Q is going to drop in energy until it reaches the bottom, where it becomes at equilibrium. This situation is also described by a delta G being positive. Now remember, the delta G is describing the forward reaction. So if we were to start here at Q and go a forward reaction, we would be going higher in energy, and that's not spontaneous. But the reverse reaction would be spontaneous. So the reverse towards the reactants would go lower in energy, and that would be spontaneous because, again, in that situation, Q is going down in energy, going towards the reactants and reaching K equilibrium. In another example, for the same situation or same reaction, we can see a situation where Q is less than K. This is a pre-equilibrium situation where we have too much reactant A, and that will shift towards product B to become lower in energy. Here, we have our system that's pre-equilibrium. We have too much reactant, so it is on the left. So here's a situation where Q is less than K. And in order to reach equilibrium, Q needs to shift towards the product so that Q can reach K. So more and more product are going to start forming, the reaction is going to shift to the products, and eventually Q is equal to K. In this situation, delta G is negative because the forward reaction is going down in energy. The reverse reaction will be positive, which would be non-spontaneous. So here we have a situation where Q is less than K, it shifts to the right, the reaction shifts to the right so Q can reach K. And the forward reaction is spontaneous, given to us as dictated, I guess, by a negative delta G. And the reaction would shift until Q is equal to K, and we are at equilibrium. We could also look at a situation where we have a reaction where K is on the product side, and that's all right. It actually does not matter where the lowest energy is. It could be on the right side, it could be towards the reactants on the left, it could be right in the middle. It doesn't matter. What's important to us is where Q is relative to K. So in this situation, we would have a Q where that is less than K, and at that point, our reactants would be too high because Q is less than K, and our forward reaction is spontaneous. So again, we are up on the left-hand shoulder, and so the reaction would shift to the right until Q reached K, and then we would be at equilibrium. From our previous class, we looked at an example of water evaporating that had a KEQ associated with it of 0.0313. This is a situation where we have a small K equilibrium, so it's less than 1, so it's on the left side of our reaction. We have more reactant than we have product, so if we divide by a larger number, we get to a fraction. So our equilibrium lies on the left side. And it's hard to see, but Q is equal to K at the bottom of this well, and that's at equilibrium, where delta G is equal to 0. On the left side, this is water evaporating. So if you have all liquid, you're on the left side of your reaction. We have too much reactant, and the system needs to shift to the right in order to reach equilibrium, and as that happens, you're getting more and more product, which is more and more water in the gas phase. This is the thermodynamic reason for why water evaporates. All of these slides are shown more clearly on OnCourse. In a previous lecture, we have discussed how to calculate delta G naught using this equation negative RT ln Q. But you can actually calculate delta G from tabulated values as well using this equation, where the sum of the free energy values is equal to the sum of the free energy products times their coefficients minus the sum of the free energy of the reactants times their coefficients. So we're going to do in example 20 is consider the dissolution of magnesium carbonate as it dissolves into magnesium ions and carbonate ions. So we're going to calculate delta G using the values from a table. This table will be provided on OnCourse, but if you want to take a moment, we're going to be using these values for the rest of this example, where we have magnesium carbonate, our delta G values for that, which is our reactant, and our products, which are magnesium ion, or rather magnesium 2+ ion, which is right here, and over to the side, our carbonate anion, which has a delta G shown here. When we bring all those values into our equation, we have the delta G is going to be equal to our products summed, so that's going to be negative 454.8 kilojoules per mole plus negative 527.9 kilojoules per mole minus our reactant, which is negative 1028.1 kilojoules per mole. And we can solve for the delta G for this reaction is 45.4 kilojoules per mole. This is a positive value, so delta G would indicate that it is an endergonic reaction, which is not spontaneous. We can also calculate our changes in enthalpy and entropy for this reaction using the same chart. So if you want to take a second and pause, you can get the values for magnesium carbonate for delta H and delta S. You can get the magnesium 2+ ions, well, rather the 2+ ions aqueous for delta H and delta S. And you can get the carbonate anion aqueous for delta H and delta S. When we calculate, we need to account for our units. So here are the delta H values that we just pulled from the table. Negative 111, negative 466, and negative 677, and those are all kilojoules per mole. The values from the table for entropy are shown here, 65, negative 138, and negative 56, all in joules per mole per Kelvin. So our values for free energy, delta G, and the enthalpy, delta H, are all in kilojoules per mole. So what I do is I convert our delta S from joules immediately into kilojoules. The other way of doing this would be to first calculate the change in delta S and then convert it to kilojoules. Either way you get to the same answer, but you must make sure that everything is in kilojoules. So the delta H for the reaction, we calculate our products added together minus our reactants, and we should get negative 32.3 kilojoules per mole. The delta S for the reaction is our products in kilojoules added together, and we subtract our reactant in kilojoules per mole per Kelvin, and we get a delta S that is equal to negative 0.2609 kilojoules per mole per Kelvin. Now, we've discovered what our delta H and delta S for the reaction is. Can we deduce the sign of delta G based on these values without doing any math? can we determine if this is a spontaneous reaction or not? Well, delta G is going to be equal to delta H minus T delta S. We have an exothermic reaction. Heat energy is leaving, so we have a negative sign for delta S. Our delta S for the reaction is negative, so we are increasing order, we are decreasing disorder. So that gets a negative sign here. So if you have a negative value minus a negative, no, we cannot actually tell if that's always going to be positive or if it's always going to be negative. So we need more information. Turns out that is a temperature-dependent value. The situation where we have an increase in disorder, if this were positive, that would be a negative minus a positive, which is always negative. If we had an endothermic reaction, that would be a positive here, and a positive minus a negative is always positive. But this is one of those situations that is mismatched, and we need more information. What we're going to do now is calculate delta G from these values. If no temperature is given, you can assume 298 Kelvin. Our temperature definitely has to be in Kelvin because that is what our units for entropy are in, or include. The assumed temperature, 298 Kelvin, is about 25 Celsius, which is considered room temperature. Kelvin is equal to Celsius plus 273. So delta G is going to be equal to our delta H value, negative 32.3 kilojoules per mole, minus our temperature, 298 Kelvin, times our change in entropy, negative 0.2609 kilojoules per mole per Kelvin. Our Kelvin cancels. This is why we always need to have our temperature in Kelvin. And what we're left with are two values that both have units of kilojoules per mole being added together, and we get a delta G that is 45.4, which is the same delta G that we calculated at the beginning of the example, 45.4 kilojoules per mole. And this should make sense because all of these values are interrelated using this equation, delta G equals delta H minus T delta S. Moving on to our next set of notes, we're going to be discussing precipitation and dissolution and introducing a new term. So solubility varies in degree, and equilibrium constant for solubility can give us an idea of how soluble a compound is when dissolved in water. This is termed KSP. This is an equilibrium constant that is called the solubility product. And this is used exclusively for reactions where you're beginning with a solid and you're dissolving it. So we're going to be seeing a few different K equilibriums. All K equilibriums are equal to concentration of products over reactants. What we've been using so far is one that is sometimes called K sub C, which is for concentration. And this is just when you have all things in solution. Sometimes it's called Kc, but I will always just be calling it K equilibrium because that's the more common version. KSP is what we're going to be discussing today, solubility product. And in the future, we're going to be doing acid-base chemistry, and those are going to get their own equilibrium constants, Ka and Kb. First, we're going to look at an example of lead dichloride, which is a solid, dissolving into solution to form lead 2+ ion aqueous and 2 chloride ions aqueous. This is enough to show that we have a solid dissolving in water to make aqueous solutions. We do not need to show water. Going from left to right, this is what we've discussed previously in class. This is dissolution. Going from right to left, that is the two ions coming together to form our reactant, which is a solid. That's called precipitation because we have things coming together and coming out of solution. Our KSP is always going to be products over reactants. For this reaction, it's the concentration of lead ion times the concentration of chloride ion squared. The chloride has to be squared because it has a 2 coefficient. So it is the chloride raised to its coefficient. Our reactant, lead chloride, does not appear in our KSP equation because solids don't have concentrations. This is a solid, it is not part of the aqueous solution, so it's not included in our solubility product, KSP. A small KSP value is going to have a large negative exponent. That's a situation that favors the reactants because we have more reactant and less product in solution. A very large solubility product is going to have a small negative exponent, and that favors the product side. And we consider that more soluble because in these situations, when you have more products, you have more stuff in solution. So if you have a large KSP, you might say that the reaction is a more soluble product. So let's look at an example. Example 1, the concentration of calcium in a saturated solution of calcium fluoride, or fluorite rather, is 2.15 times 10 to the negative 4 molar. What is the concentration of fluoride? What is the solubility product of fluoride? Well, we need to find KSP. In order to figure that out, we need the concentration of products. Remember, in these situations, for KSP, the reactants don't factor in. So here's the reaction. CaF2 solid is in equilibrium with the calcium 2 plus ion in solution aqueous plus 2 equivalents of fluoride aqueous. We're given the calcium 2 plus solution in the word problem, and we can calculate our fluoride this way. So here we have 2.15 times 10 to the negative 4 moles of calcium ion per liter of solution, that is our molarity, multiplied by 2 equivalents of 2 moles of fluoride for every 1 mole of calcium. That comes from our reaction where we have 2 equivalents of fluoride formed for every 1 mole of calcium formed. By multiplying by this term, we can cancel our moles of calcium with our moles of calcium, and what we're going to be left with is moles of fluoride divided by liters of solution, which is molarity. So 2.15 times 10 to the negative 4 times 2 is 4.30 times 10 to the negative 4 moles of fluoride per liter of solution, which is molarity. We can now calculate our KSP. That is just going to be equal to the concentration of our products raised to their coefficients because our reactants are solids. So KSP is equal to the concentration of calcium 2 plus ion times fluoride squared. That is going to be 2.15 times 10 to the negative 4 molar, given from the problem, and multiplied by 4.30 times 10 to the negative 4 molar, which we just calculated, squared. Always remember your order of operations here. You need to square this term before multiplying by the calcium. If you do that correctly, you should have a solubility product that's equal to 3.98 times 10 to the negative 11. In example 2, we introduce a second new term. So in example 1, KSP is called the solubility product. In example 2, we're going to be calculating the molar solubility of something. And molar solubility you can think of as solving for X using an ice table. So here we have calcium hydroxide. And calcium is a 2 plus ion because it is isoelectronic to argon. And hydroxide is a 1 minus ion, which we can get from its Lewis structure. When oxygen has an octet, it has 7 valence electrons around it, which is 1 more than it's supposed to have. So it has a negative 1 charge. Calcium hydroxide is then written as calcium with 2 equivalents of hydroxide to balance out the charge. Solid is in equilibrium with calcium 2 plus aqueous and 2 equivalents of hydroxide aqueous. The KSP, which is given, is 6.5 times 10 to the negative 6. So when we're filling out our ice table, we put in all of our species at the top, but calcium hydroxide is a solid, so it has no concentration ever. So we don't have anything in that column. Calcium 2 plus and hydroxide go in our second and third columns. At the initial point, neither of them have a concentration. Calcium is going to go up by X. Hydroxide is going to go up by 2X because of the 2 coefficient, which leaves us with X and 2X at equilibrium. When we solve for X, we have KSP is equal to the concentration of our products raised to their coefficients. So we have calcium 2 plus times hydroxide squared. Our KSP is 6.5 times 10 to the negative 6. That's going to be equal to X times quantity 2X raised to the second power. That is equal to 2X squared is equal to 4 times X squared. And when we take 4 times X squared times X, we get 4X cubed. So we have 6.5 times 10 to the negative 6 is equal to 4X cubed. We divide both sides by 4 to get 1.6 times 10 to the negative 6, X cubed. And we take the cube root of both sides to solve for X. The other way of doing that is, which might be easier depending on what kind of calculator you use, is to take 1.6 times 10 to the negative 6 raised to the fraction 1/3. That gets you to the same thing. X is then equal to 1.2 times 10 to the negative 2, and that is our answer. That is our molar solubility. The question asks for molar solubility, and we found that by calculating for X. We could then use our molar solubility to tell us what the concentration is for calcium 2 plus, which would just be 1.2 times 10 to the negative 2 molar, or the concentration of hydroxide at equilibrium, which would be 2 multiplied by our molar solubility. And that's the end of the material for today.